All right, let's take a look at the physical properties of some of the molecules we've been talking about, the alcohols, phenols, ethers, and thiols. And to start out, we're going to look at the most important of these groups. That's the alcohol. So alcohols have some very, very unique properties. If we were to just draw out a simple alcohol, such as methanol, what we'd find is, if we sort of zoomed in on the oxygen, there are two non-bonding pairs of electrons on the oxygen. And the general shape of the oxygen actually is fairly close to tetrahedral geometry, like you would see with a carbon. Notice, though, there's only two bonds coming off of oxygen, and that's because oxygen has 6 valence electrons. To get to its octet, it only needs 2 more. So the bond angles of alcohols tend to approximate the tetrahedral geometry. They tend to be a little bit squished from the ideal 109.5 because these electrons tend to spread out a bit more. So the geometry tends to be between 104 to 105 degrees, depending on the nature of the actual alcohol. So the shape is important, but one of the real key features about alcohols is they have this very electronegative oxygen. So because oxygen is highly electronegative, let me redraw this molecule. I'll leave off the electrons here for now. Because this oxygen is highly electronegative, it has a partial negative charge to it. So it's pulling electron density away from whatever it's attached to. So in essence, what it's doing, it's sucking the electrons away from this hydrogen, making this a partial positive part of the molecule. So because there's this difference in distribution of electrons between the two atoms, we call this a polar bond. And we'll often indicate this with a polarity arrow that looks like this. When you draw a polarity arrow, you usually point it towards the direction of the more electronegative atom, and then you put a little crosshatch, looks kind of like a plus sign, next to the atom that is partially positively charged. Now, not only is there a polarity arrow from the hydrogen to the oxygen, there's also a polarity from the carbon to oxygen. So there would also be a polarity arrow here, and this carbon would be partial positive charged as well. So the overall polarity of this molecule, you treat it similar to what you do with vectors. These two vectors are both pointing towards the oxygen. So the overall polarity of this molecule, if you were to add the two vectors together, would look like that. All right, so the polarity and electronegativity of the oxygen really gives some very unique properties to alcohols. The main ones being hydrogen bonding. So this right here, this polar OH bond, and the presence, I'll go ahead and put these in now, of the two lone pairs of electrons on oxygen, allow alcohols to exhibit the property called hydrogen bonding. So if I were to redraw this again, our methanol molecule, and orient the partial positive and partial negative charges next to another molecule of methanol. So let me draw now a hydrogen bond between this hydrogen and the oxygen of another methanol. Okay, so again, here's one molecule of methanol with a partially plus H. It can form a weak interaction, indicated by this dashed line here, called a hydrogen bond. And notice that in order for a hydrogen bond to form, it has to have an acceptor oxygen that has two lone pairs of electrons on it. So methanol can form a hydrogen bond in this way with this particular molecule, but notice it has two lone pairs of electrons here that it could actually form hydrogen bonds to two other methanol molecules as such. So if we were to compare and see what the effect of hydrogen bonding is, the main effect is going to be on the physical properties, things like melting point, boiling point, solubility. So if we were to compare ethane to methanol, okay, the size and atomic mass of these is almost identical. If we were to look at the boiling points, let's say, okay, so the amount of energy or amount of heat we'd have to put to get this from the liquid state into the gaseous state. So ethane has a very, very low boiling point, okay, down around minus 80 degrees centigrade. So at very, very cold temperatures, this thing's already a gas. However, methanol, because it has the ability to form these hydrogen bonds, has a much, much lower, or I'm sorry, much, much higher boiling point. This is about 60 degrees centigrade. So you can see just by having this OH group, this very polar group that can also have these lone pairs of electrons to form hydrogen bonds, significantly affects the abilities of these things to boil. Another physical property that's affected by alcohols is what's called the solubility. So solubility is the ability for a molecule to dissolve in water. So compounds like butane, pentane, hexane, these sort of these alkane or just hydrocarbon-like molecules, if we were to look at the percent solubility in water, this essentially has 0% solubility. There is a very, very slight solubility of something like butane or pentane in water, but it's very, very minuscule. But when you convert one of these methyl groups into an OH, something like propanol, now our solubility will go almost through the roof. So this particular compound has about 95% solubility in water. So what that means is we can add, if you had 2 beakers, you could add 95 milliliters of propanol to 100 milliliters of water, and they would essentially be completely miscible. Now, as you start to extend the chain, so now I have 1, 2, 3, 4, 5, we get to pentanol, we'll see our solubility actually will start to go down. This is about, actually it's closer to 60%. Okay, if we add 1 more carbon, okay, so now we're out to 6, this goes down significantly. So now we're down to about 5%. And when you get to something like heptanol, it goes down to only 1 or 2%. So this ability to affect the solubility of a compound by having this OH, it definitely does decrease as we increase the hydrocarbon-like nature of the chain. But the presence of this OH group with its lone pair of electrons essentially allows hydrogen bonding to occur between these and water. So if I were to just draw out a generic alcohol here and showed how it's going to hydrogen bond with water, notice water is very similar to an alcohol itself. It just has a hydrogen instead of an alkyl chain. But here we would have a partial positive H, partial negative oxygen, so we could form a hydrogen bond there. Likewise, on this same alcohol molecule, we could form a hydrogen bond to another molecule of water, like this, where the hydrogen is actually forming the hydrogen bond with the oxygen of another water. One final definition I want to get in here when I talk about hydrogen bonding. We need to talk about hydrogen bond donors and acceptors. A donor. Hydrogen bond donor is the heteroatom, in this case oxygen, that has an attached hydrogen. So this is the donor in this particular hydrogen bond, and the acceptor is the heteroatom that has a lone pair of electrons. So this is the acceptor. So in the case of an alcohol, there are 2 sites that can act as acceptors, the 2 lone pairs, and then this would also then be called a donor, the hydrogen attached to this oxygen. So notice that you can differentiate between the directionality of a hydrogen bond by invoking these 2 terms called the donor and acceptor. So I hope that helps out with physical properties of alcohols.